Section 15.2, energy in simple harmonic motion. Because we got to get back to energy. It has the best units, right? All right, so we can write functions to express the potential and the kinetic energy now as functions of time, right? We already know our elastic potential energy is 1/2 kx squared. That's nothing new, but if we plug in how x, displacement, varies with time, we get that our potential energy as a function of time is 1/2 k x max squared times cosine squared omega t plus v. Similarly, we know our kinetic energy is 1/2 mv squared. That's nothing new. But we can plug in our expression for velocity, which is just the first derivative of position with respect to time, and then we get positive 1/2 k x max squared times sine squared omega t plus v. So this tells us how, if you plug in a time to either of these, it'll tell you what amount of potential energy you have, what amount of kinetic energy you have. And there's a nice graph of these on the right, which shows as time passes, the green is the potential energy, and that's cosine squared. So it starts at a max, it goes down to 0, not negative, goes back up to a max, and so on and so forth. The kinetic energy does the exact opposite because it is sine squared. So it starts at 0, again, not negative, but 0, goes up to a max, back down to 0, and up to a max. So we've lost all negative values here by looking at energy. And that makes sense because we can't have negative kinetic energy. Kinetic energy always has to be positive. Notice too that there's a max kinetic energy, for instance, at 2 points in a full cycle. Why is that? Well, if you imagine a spring and you stretch it down, it's going to get to its max kinetic energy at the midpoint as it's crossing, and it goes up to the top. But that's not a full cycle. It will then go back down through that midpoint of highest velocity until it reaches the bottom. Similarly, for the potential energy, if you stretch it, it starts out with some elastic potential energy, its max value, goes to 0 in the middle, and up to its max again at the other side, but it still needs to go back down to where it started. So that's why the potential energy curve there has 3 separate peaks. Now, if we add these together, 1/2 k x m squared cosine squared plus 1/2 k x m squared sine squared, we get the mechanical energy. And we note that the first half of these is identical, 1/2 k x m squared. The only thing that's different is cosine squared plus sine squared. If you remember from math class, cosine squared plus sine squared is just equal to 1. So we find that the total mechanical energy doesn't have any time dependence. It's just 1/2 k x max squared. And that's what's shown on the plot over here, where the total mechanical energy has a constant value for all of time. One other thing with the kinetic energy equation, I understand that you may be looking like, okay, how do we go from having an m to suddenly having a k? That seems pretty weird. And short answer, you're right. It has to do with the fact that our angular velocity is equal to the square root of k over m, and we have an omega squared in there. So omega squared times m is actually equal to k by squaring both sides, multiplying the m across. And so I'm skimming over the math here, but with that relationship, you can show that we can go from having a mass to having a spring constant k. One other thing that's useful is the plot on the bottom shows how the energy changes as a function of position, which is pretty interesting. We already have the potential energy somewhat set up in terms of position. You can imagine it's u as a function of x is equal to 1/2 kx squared. And so that's going to look like a parabola. And sure enough, our potential energy follows this parabolic shape. That as x gets bigger in either direction, we get more and more potential energy. Now, what about kinetic energy? How does kinetic energy vary with position? Well, one way we can get kinetic energy as a function of position is we can use this relationship with the total energy. So if we remember that the total energy is potential plus kinetic, then that tells us that our kinetic energy is just going to be equal to our total energy minus our potential energy. That minus sign got really big there, extra stoked. So we can then plug in that our kinetic energy as a function of x is equal to this constant that's set by the total mechanical energy, which is just our 1/2 k xm squared, and then minus u as a function of x, so minus 1/2 k x, where x is a variable, squared. And so that gives you how kinetic energy depends on position. And it can be really useful. For instance, there's a homework problem that asks you to solve for when the kinetic and potential energy are exactly equal to each other. Pro tip, it's not at 1/2 of x max. It's something a little bit different. And this might help you as you think about that. All right, so now that we've learned about energy, both potential and kinetic in this simple harmonic motion, let's take a look at a checkpoint. So it says, in the figure shown, the block has a kinetic energy of 3 joules and the spring has an elastic potential energy of 2 joules when the block is at x equals 2 centimeters. A, what is the kinetic energy when the block is at x equals 0? B and C, what is the elastic potential energy when the block is at -2 centimeters and -x max? Right, so this is a good thing to think through. So please think through it, come up with an answer to all 3 parts here. I'm going to skim through them, but please go ahead and hit pause. So this is the answers to part A, you can pause. Answers to part B, match it. And answers to part C are also the same. So please stop and think about this. Do come up with an answer to these. Right? Have you done it? Hopefully so. Okay, so the key here is that our total energy is constant. The mechanical energy is conserved. So that means our total mechanical energy is just going to be adding together 3 joules plus 2 joules. So total energy of 5 joules. Awesome. We also note that because we have this combination of kinetic and elastic, that we aren't at any of the extreme points. We aren't at the maximum range of motion, nor are we at the very middle, where x is equal to 0. So that tells us that once we get to x equals 0, where there's no potential energy, all of that mechanical energy, all 5 joules, is going to have to be purely kinetic. Then when we think about elastic potential energy, if we are at the -2 centimeters, notice in the elastic potential equation is 1/2 kx squared. So the negative doesn't matter. It just depends on how far you are from equilibrium. So it should be exactly the same as when we're at +2 centimeters, 2 joules. What about when we go to -x max? Well, at that point, the kinetic energy should be 0 because it will briefly stop. That's the turning point before it goes the other way. And at that point, we once again will have 5 joules. So we put this all together, and we do see that it is 5 joules, 2 joules, and 5 joules as planned. So that's energy in simple harmonic motion. One more section will sneak in there, 15.3, an angular simple harmonic oscillator. So a torsion pendulum deals with the elasticity from a twisting wire. So you have a hanging disc and it twists in the same way that a spring bounces up and down. So it moves in an angular simple harmonic motion, where instead of having the force is equal to -kx, we have that the torque is equal to -kappa theta, where kappa is the torsion constant, theta is the angular displacement. So it's the angular form of Hooke's law, which is pretty cool that it works this way. So we could replace all of our linear variables with their angular equivalents, and we'd find that the period of it is equal to 2 pi the square root of the rotational inertia divided by the torsion constant. So rotational inertia instead of mass, torsion constant kappa instead of spring constant K. Pretty straightforward. The neat part here is that this is actually very precise. You can check out this YouTube link to see there are clocks made on this principle. They're known as Atmos Clocks. Very expensive clocks because they're very fancy, very precise. But it twists through a ton of degrees for about 30 seconds before it starts to twist the other way. So there you have it, an angular, simple harmonic oscillator.